Good morning, ladies and gentlemen. I see that we have quite a significant audience joining. I do see that we still have a couple more people joining at the moment, but I think we could start the ESP technology webinar series. So we would cordially invite you to the webinar, Thermal Energy Storage, a key enabler to the clean energy transition. This webinar is scheduled for 1.5 hours with 2 presentations on thermal energy storage from Azaleo and Malta, followed by a Q&A session for both presentations. Before we start the webinar, I would like you to use the Q&A box to share your questions, and would encourage the attendees who ask the questions to introduce yourself in the chat box. Now, I would like to pass it on to Juliet Kumpuni, Senior Energy Specialist from the World Bank and the ESP Secretariat, for the opening remarks of the first Energy Storage Technology webinar series. Juliet, the floor is yours.
Thank you so much, Charlie. Good day, everyone, and welcome to the Energy Storage Technology webinar series, which is hosted by the Energy Storage Partnership. The Energy Storage Partnership is a global partnership convened by the World Bank Group to adapt and develop energy storage solutions for developing countries, and is hosted by the World Bank's Energy Sector Management Assistance Program, ESMA. The objective of the ESP Technology webinar series is to provide a platform to showcase some of the state-of-the-art energy storage solutions that would play an important role in the decarbonization of the power sector. The main focus of the webinar series is to inform the audience the different types of non-lithium ion solutions that are currently available in the market. We focus on technologies that are not only becoming cost competitive, but would also provide long duration energy storage solutions, which would become critical as the share of renewable energy becomes larger in the power system. We would also be announcing soon an upcoming webinar on non-lithium ion electrochemical energy storage and pumped hydro power storage, which would be scheduled for May and June, respectively, this year. Once again, I want to welcome you to this inaugural webinar of the Energy Storage Technology webinar series. Thank you so much, and please stay tuned for more information on the ESP. So welcome, and I will hand over to Chong. Thank you.
Thank you, Juliet. Thank you for the lovely introduction. I would believe that most people, when they hear the terminology energy storage, they would generally relate to lithium-ion battery energy storage systems, since this is currently the leading technology comprising most of the current market share. However, as Juliet has mentioned, as the share of the renewable energy increases in the power system, there is a need for careful energy management, as well as dispatch procedures that are needed to manage these renewable energy, but also the need for large volumes of energy storage, where long duration energy storage will play a very critical role and a pivotal role in the decarbonization of the power system. To achieve carbon neutrality, the world's electricity grids will need to deploy up to 140 terawatt hours of long duration energy storage by 2040, which would translate to up to $3 billion in investments. And that is an immense task that which is borne upon us. Recently at the COP26 summit, the Long Duration Energy Storage Council was launched with the purpose of guiding governments and grid operators on how these technologies will support the decarbonization of the grid as the lowest cost option. For this webinar, we had invited 2 innovators, Azaleo and Malta, who are the members of the Long Duration Energy Storage Council. They will present the state-of-the-art technologies related to thermal energy storage and its role in the energy transition. We first have Torbjörn Lindquist, who presents Azaleo's thermal energy storage, Torbjörn Lindqvist is operating as the CTO as Azelio AB and is a member of the management team. In his role, he has led the development of the test pod system from basic idea to a commercial product. He is also responsible for IP matters and establishing external and internal research and development projects and networks, supporting the development of the product and business. Prior to joining Azelio, he has received his PhD in energy science from Lund University in 2002. I would stop here and pass it on to Torbjörn. The floor is yours for the first presentation. Thank you.
Thank you so much, Chong. I'm just going to share my screen. Do that like this. So thank you very much. I'm Torbjörn Lindqvist, and I've been with this company now for 6 years developing this product. Azelio is in the game of energy storage to actually support the growth of the renewables in the world. I have 25 minutes and I will start with a little bit about renewables and storage in a global perspective, how much is being done today and the reason why we have a potential business in this sector. And then I will talk about our technology, the customers that we have signed contracts with, and also a few business case scenarios that we've looked for a number of cases. But just to set the frame of what Azelio is. Azelio is a Nasdaq First North listed company in Sweden, Stockholm. We have about 250 employees. We are in the phase of having a commercial product, ramping up sales volumes to a number of customers. We have our main operations in Sweden, in Gothenburg, Uddevalla, Åmål. And then we have business development in Spain. We have offices in Morocco, South Africa, Australia, and also China, Beijing. If I then start with why are we here? This is a well-known graph showing the difference between when renewable energy sources actually do produce from PV panels. Wind turbines are not shown here, but that adds another dimension to this graph. But looking at just PV panels, the match with demand, if you look at residential demand, is different from what PVs can deliver. If you look at industrial baseload demand, also customers that we are talking to, it isn't a good fix either. So you need to fully utilize and fully decarbonize those industries and communities. You need to have a means of energy storage, and that's what I'm going to present today. And if you look at what is happening in the world, there's a huge investments in maybe on an annual basis around $500 billion in various renewable systems like renewable energy, electrified heat, transport, and carbon capture and storage. But only a fraction of that, 2 orders of magnitude lower, is actually invested in energy storage, and that is way too little. It needs to ramp up significantly to actually balance off the huge investments in renewables, wind and PV, for example. And so long duration energy storage, not the 2, 3, 4 hours, it's the 10 hours and plus that is really the demand now for the world and for the energy systems. If we look at more near term, what needs to happen up until 2025, or what the general view is, or is assumed, that we need to reduce CO2 by 1.5 to 2.3 gigatons of CO2 by 2025. And to do that, we need, or perception is that we need to install a terawatt hour in renewables and in energy storage by 2025. And looking at where we are now, we're only 7%, and 2025 is rapidly approaching. So we need to invest and develop these technologies, and this is the rationale for us, and that's what's driving our business. And looking even further away, 2040, the demand for energy storage is like hundreds of terawatt hours. It's a lot more. It's a 2 order of magnitude more than we need 2025. If we then look at the Long Duration Energy Storage Council that we are a member of, and also Malta, I mean, we have in that group classified kind of what is long duration energy storage. And as Juliet mentioned, the batteries and the pumped hydros, we'll have other web seminars in the future, but we are in this box, the thermal one. And here we have all the sensible heat, the latent heat, where you have store energy in phase change materials. And you do the conversion with either heating, resistant heaters, and then you do the power conversion back to electricity from a thermal engine. It could be any turbo machinery, it could be a Stirling engine, it could be a heat engine. So there are a lot of different technologies within thermal, but it's the governing thing for thermal is that you store heat in a thermal media. That could be rocks, melting metals, etc. When you look at mechanical ones, that's when you liquefy gas, CO2, you compress air and store that in large caves, and then use turbo machineries to convert that back to electricity. Chemicals, that's hydrogen. Electromechanical is flow batteries, to just very to summarize that. If you look at then, there are services that provide heat only. That's not our solution. There are services that only provides electricity, like batteries and flow batteries, etc. And there are solutions that actually can provide both. We have electricity from our system, and we can also provide low temperature heat up to 65 degrees C. So we would put ourselves in an area where we can actually supply the customers with two energy media. And we're operating from a storage capacity from 13 hours and upwards. Or the system is designed for 13 hours, that I will show you in a few slides. This is the system that we have worked up over the last couple of years, starting from nothing. The only heritage we had was the energy conversion unit, which is a Stirling engine. It's around 13 kilowatts of power. And to balance that, we then store energy in this box by melting a aluminum alloy at a temperature of around 600 degrees Celsius. And this is scalable. So each unit is 13 kilowatts of power, and that's what you have. That's the standalone module. And if you need more power, 250 kilowatts, 1 megawatt, you just have a number of those in clusters, and that's what we are offering to the customers. So it's sustainable because we have no, the only thing we have in here is aluminium and silicon, and which is not harmful, and there's plenty of that in the earth, and it's modular, scalable. And when we do the economics to calculate what the electricity costs, we would claim that we are cost competitive to batteries and other non-renewable alternatives like diesel. And together with PV, we can supply customers with electricity 24/7. So PV during the day, and then stored heat and converted back to electricity at night. So the charging is in this example, for example, we have the PV field that we design both supplies energy during the day to the customer. As a backup, when there are no renewables, we would either have to be grid connected or having a backup DC genset. But the PV panels also charges the energy storage modules during the day, and at night during discharge mode. This storage is designed to cover for most of the electricity needed by the customer here. So that's the 24-hour cycle. So PV charging both the system and the storage during day, and then discharging at night. When we have looked at economics, we say that batteries are about 40% cheaper than a diesel generator only powering cycle, and we would be something like 60% cheaper than the corresponding diesel gensets. So there is a cost alternative, but then you could also argue from a lithium-ion battery, is that a long duration energy alternative, or is that a best technology for short durations and for frequency and voltage stabilization? But that's a different question that we can have a debate later on. But this is a solution that is being designed for long duration, 13 hours of energy storage to cover the night. When we do the life cycle analysis to see what's the impact of CO2 equivalent throughout the life cycle, we would, depending on how many batteries you would need to change over the lifetime, it's about 30% less CO2 emissions than batteries, and about 96% cleaner than the diesel genset. But that's an obvious one because that only emits CO2 from the diesel it's burning. It works like this. So it's charged by electricity by melting the aluminum alloy. We have about 4 tons of that in here. So it changes from solid phase to melted phase in a container, and it's heated from underneath. Once stored, so everything is then melted, when we want to convert it back to electricity, we pump sodium, melted sodium, around the storage that is being, so the sodium is heated up, and then that heat is being used in the engine to produce power. And that is available on demand. You can start one, operate a part load, or you can have every single unit engaged in your system, in your park. So this is the basic idea that we have developed everything on our own, everything from pumps to engines to the storage technology. And we're backing up by 16 granted patents in this area. If you look at one customer example, you can optimize and you can model that in many different ways. You can look at how much of the electricity from the PV panels, if that's their energy source to charge it with, how much is that going on a daily basis? If you look at the wind and weather data, how much of that is being used to charge your test board, which is the red one here, and the other one supplies the demand. And then you can look at the over a year, how much of the total energy is being provided by the PVs and how much is being provided by the test pod on an annual basis. And then you can look at the deficit, how much extra power do you need to supply from other energy sources like the diesel gensets. And then you can optimize this depending on your objectives. If it's to minimize CO2, minimize cost, minimize the independence of the grid, etc., you will end up with a different results here. And then you can dive into each day by day. How does it look like? What's the production profile from each of these sources? And you can look at what's the state of the charge of the battery, and what's the energy production over the day. We have a number of verification projects. We have our own lab in Åmål in Sweden, where we do most of the development and testing internally. We have done tests and development and in collaboration with Mazen in Morocco at the North Solar Power Complex. We have also now recently inaugurated a research facility together with Khalifa University in Masdar in Abu Dhabi. We inaugurated that in January this year, and we have ongoing tests there to validate its performance and endurance and availability. And together with that evaluation, we're working with DNV and they are a third-party evaluator to confirm what we measure and make sure that it's in a proper state. Our key target sectors, that's what we say communities, either connected to the grid or in island operation without any or in a weak grid connections. We have commercial facilities who are looking to decarbonize and looking for 24/7 options. We have lots of work with mining industries, extraction industries, and production ones. And they have an extreme environment in remote locations and not necessarily connected to the grid. We have recently sold one to in South Africa, which is in agriculture application for crop production, etc. And we're also looking at water, so powering desalination plants and even using the heat that we produce to produce desalinated water. So these are target sectors that we are looking for. And for commercial projects, we have one unit in the solar park in Dubai, which is the Rashid Al Maktoum Park. And that's there to power the visitor center or the solar park there in Dubai. We have also a local customer in Sweden, industrial facility, where we have 2 units taken into operation in a few weeks' time. And that's to power the industrial facility. And we have also ongoing installation in South Africa, and that's what I mentioned in the previous slide. It's an agricultural farm. This one is estimated to reduce the CO2 emissions by over 300 tons on an annual basis. Looking at another picture of the Master Abu Dhabi unit, here you can see it's quite close to residential areas, and it's in the middle of the solar research facility that they have at Master Khalifa University. And these are the 2 units that we have there, and this is another one. So the engine and the cooling fan is here, and what you see in the background here is the actual unit and an electrical cabinet. And here you can see a pump that pumps the sodium, which is our heat transfer fluid in our system. So the WeBe system that we have sold, it is designed to provide them with 24-hour clean power every day, and quite a few tons of CO2 reduction every year. And that is in South Africa, and the business model there is that we have set up a holding company owned by Azelio, and that's the business model that we're using. So we are the technology provider, and we operate in 2 models. Either we set up a company that owns the facility and we operate an energy as a service contract with the customer, or we can do a direct sales. But as you all possibly know, that in the early phases, like a company like us, it's very difficult to do for direct sales directly. So you need to take some ownership of the projects that we are launching. And that's why we have different business models in the beginning. But the long-term aim is to do direct sales only to the end user of the systems. And then we are setting up a service offering that we do training and support and service with local companies in the world that we are operating. If we go for another example from mining, in this one their alternative fuel was diesel and grid power, and doing the CO2 balance calculations, we are 75% clean of that, and based on the cost of electricity from our system for that particular customer with 40 units in operation, so it would be PV panels and our systems, we would save the customer $1.6 million on an annual basis. As an example for mining industries, and we have modeled quite a few of these, and we are in discussions with potential customers there. If you look at agriculture, a similar exercise where we have the same amount of units, 40 units, it's 81% cleaner, and then what we reference case here is a grid connection of wood fuels, and that would save them somewhat less than $1 million per annum. We have another one with communities. This one is slightly smaller. We would have 20 units in combination with solar PV, and that would be 84% cleaner compared to diesel application, and save them about $345,000 per annum. So this is an introduction to a technology that we have developed over the last 6 years. The company has been there for a few more years than that, but then we looked at other applications of the Stirling engine. And this is one of the many technologies that are being developed in the world as we speak, targeting the long duration energy storage. And I would say that now our system is installed in a few places in the world. We're operating it. It's being CE certified, validated by DNV. And we have established a supply chain in Europe, in Northern Europe, I would say, mostly. But that is then, if we ramp up in volumes, when we do that, we can copy paste that business model to other places in the world to have a local manufacturing of the technology. So we aim at doing as little as possible. We do assembly in Sweden, but the manufacturing and the components that we use sub-suppliers for. And the first commercial product have been launched and are operating as we speak. So this is one solution. I'm happy to answer questions later on, but I'll hand back to John. Thank you.
Thank you so much, Torbjörn. I see that we have a very diverse audience from all the way from Ukraine all the way to Zanzibar, and I do see some familiar faces in the audience also. And also I do see a couple of questions that have been posted in the Q&A box. I will first take them step by step. So what I'll do is I'll do it in batches, and then we can answer the following questions accordingly. So the first question that we have received is regarding the temperature. Which one is the minimum temperature for your technology? This is posted by Alejandra. And then the second question is, what is the cost per kilowatt hours of this system, posted by Pratik? So Torbjörn, could you please answer these questions? Over to you, please.
Yes, we have, with regards to temperatures, we melt our phase change material, which is the energy storage material, with electricity, and this material is a eutectic material, so it's a combination of aluminium and silica, and that eutectic material, it's commonly available. It melts at 577 degrees C. So we use the latent heat. So we use, when it then freezes or converts back to solid state, that's the latent heat that we extract and heat the engine with. So that's a constant, almost constant temperature throughout the discharge cycle, and that is the temperature and the heat into our Stirling engine that then operates. So that's the upper limit that we could get, 580 degrees C, and that's a constant temperature throughout the discharge cycle. And then the bottom temperature, because it's a thermal engine, it's cooled by ambient air. If we cool it with water from a district heating system, I mean, if you look at the fourth generation of district heating systems, they typically operate between 55 and 65 degrees C. So if you take that water, the return water, and cool it with that, you can then produce an additional benefit, which is heat, So that would then set the low temperature of our heat engine. So anything from ambient temperature as a lowest reference temperature up to 600, almost 600 degrees C as the highest one. So that is a little bit about temperatures we have in our system. And designing this, we really had to decide what the appropriate temperature would be for the engine. If the higher you go, the more challenging it is with the high cost materials and temperatures. But on the other side, the efficiency would be higher, but that always comes at a cost. And so there's been very detailed considerations where to go with that design parameter. Just remind you, the second question was, John.
So the second question was the cost per kilowatt hour of the system. Yes.
We have if you look at just the LCOS number, levelized cost of storage, that's around 890 euros per megawatt hour. And the levelized cost of electricity is slightly higher if you look at just that. But that incorporates levelized cost of electricity, that then is the 24/7 offering. So you have PV during the day and this storage technology at night. So it's the combined cost of that system, which is around $90 per megawatt hour.
Thank you very much, Torbjörn. So following the questions related to cost, I think there are a couple of more questions which are relevant. So I would address those. So there is a question from Dick asking of what the cost of the basic 13 kilowatt module, 13 kilowatt hour module is, and how does the cost comparisons calculations take into account lower round trip efficiency of Azelio technology compared to lithium-ion technology. And this has been asked by Alexandra. So over to you, Torbjörn.
It's a good question, thank you. Typically, the cost of each unit, we don't disclose that publicly. That's something we discuss with customers and also like on each case by case with them. But we do estimate for, I mean, what I said about the LCOE number, the $90 per megawatt hours, that should be then compared with battery and alternative costs. And we are based on our calculations, but I also appreciate that doing these calculations is, I think a lot of people and companies and customers around the world are actually doing these calculations as we speak. And that's very much dependent on the lifetime of the batteries, what's the depth of discharge you can do, what's the end of life capacity of a battery. And so this is all about if you want to cover 12 hours, how many sets of batteries with a C ratio 1 to 4 do you need? Do you need 3 units? And so the answer is you need to know all of these questions to these design parameters to design a battery equivalent system for long duration energy storage. And then you also need to take into account end of life costs with dealing with what's left. We say that we have aluminium, there's nothing harmful with that, you easily recyclable, and it has an asset value at the end of lifetime. So taking all these things into account, which is, and all of these are uncertain, we know exactly what we have, the production time, degradation, and tapering effects during a discharge cycle. We would claim that we have a good margin to equivalent battery offering on the market today. But I wouldn't say that one is better than the other. I would say that in the long duration energy storage council, that we say that all the technologies that have been developed do have a marketplace out there. So no one is, I would say, better or worse than the other. They have all different means. mean, there's no way we could compete with batteries when it comes to frequency and voltage stabilization, because that's what batteries are designed to do. They're very rapid. They respond in milliseconds, and they can control. We don't do that. We act as a base load power source during the night, so covering the base load, and then we could complement that with battery packs to cover for variations in the grid. So it's a simple question to raise, and it's a very difficult one to answer. But I think I've kind of elaborated a little bit about the answer.
Thank you, Torben. Actually, this is a question. This is a question that is being asked by a lot of people on what is the cost competitiveness of long duration energy storage. But I think my stance on this, and I believe that this will be a stance of a lot of people in the energy storage arena, is that we would need all types of energy storage technologies, starting from short duration, medium duration, long duration energy storage, as well as seasonal energy storage, because we are actually looking into approaching towards a net zero strategy for a lot of our countries. And in fact, the thermal energy storage becomes really competitive in the long duration energy storage arena, because we can then deploy a lot of renewable energy in the system, and we don't have to worry about the balancing the intermittency of renewable energy, because we have massive amounts of energy that can be stored, as opposed to lithium-ion technologies that are more customized to provide the short duration and the grid flexibility support, which is needed for 1 hour up to 4 hours, which is the kind of the time range that they are cost competitive. So I would also like ask a couple more questions. I see that there are a lot of questions. I'm trying to address all of them, but there is a question from Giuseppe. I'm not sure if I pronounced it right. Apologies for that. What is the HTF used in your system? And then there is a question about the percentage of daily self-discharge of Azalea's test pod, and also the round trip efficiency from for power to heat to power application. I would, Torbjörn, over to you, please.
Yes, thank you. The heat transfer fluid is, we've investigated that a lot. When we first started off this a few years ago, we were very much focused on salt. But we couldn't get that to work at these temperatures that we were looking at. And the only other alternative that we could see was sodium. So it's well known from nuclear industry. They have a long experience of sodium-cooled reactors. So we have a small amount of sodium in our system. It melts at 100 degrees C. It vaporizes at 880 degrees C. And we're operating at around 600 degrees C. So it doesn't corrode the pipes and the construction materials we have in there. It's an excellent heat transfer material. The only thing you have to cater for is to avoid oxygen coming into the system, and also not having any water whatsoever, because it's highly reactive with oxygen and water. But as long as you keep it in a safe environment, it's a perfect heat transfer fluid, and it transfers the heat from the storage to the engine in a very good way. The round trip efficiency it's set by Carnot efficiency for these types of heat engines, and that applies to all engines, even the ones that Michael later on is going to talk about. It is 600 down to 30 degrees. It is 30% efficient with the turnaround efficiency. And we're working on future technology that we will deploy in a few years' time, completely different kind of one part of the system will be different, and then we can maybe push that up to 35%. So we'll be continuously improving that efficiency. And a lot of people might be put off by such a low efficiency, but you have to look at the costs and the environmental impact of the complete system and do the economic calculations to see, even though we need to oversize the PV system to charge it to cover up for the low efficiency, we still have a very competitive levelized cost of electricity. Because it's thermal storage, we have 4 tons of melted aluminium in there, and the operational philosophy is to turn that around on a daily basis. It's not designed to charge one day the first week of the month and then discharge that at the end of the month, because then it will be quite expensive. You need to operate your system and produce power to show those good levelized cost of electricity numbers. But even so, on a daily basis, we have something like 2 kilowatts of heat losses per continuous. And if you multiply that with 24 hours on a daily basis, we lose something like 50 kilowatts, which is about 10% of the heat on a daily basis. So that's the heat losses. So if you have it stand still for a week or so, you can then calculate how much energy you would lose. So preferably you would then have it operating every day. It's a balance. You could insulate it more with more perlite, but then the cost of that would go up, and we have carefully considered exactly what and how much perlite we would need to insulate our system. Okay.
Okay. So another question is from Said. Could you provide a few insights into the O&M of the system? And there's another question from Kingsley. What is the typical size of the load that your unit serves? Yeah.
We have operation and maintenance. We have a we designed it for 30 years of life. That's everything is designed for that. We have an annual or every 6,000 hours we have an engine overhaul to change the wear parts, but that's on an annual basis, more or less, or a little bit more than an annual basis. On an operational point of view, we have designed it for installing 40 of our units, and that we call a cluster, and then we have a cluster controller. And so if there is a demand, that goes into that cluster controller, and the cluster controller has full control of the state of charge of every unit, and then requests power from those 40 units as and when needed. And then when you charge it, again, the cluster controller manages that too. Each unit can be powered by 100 kilowatts of power, so you can actually charge it in 6 hours during the day, and then you discharge it at for 13 hours at night. And this is, you can of course charge it with lower power as well, less than, but then you need to charge it with more power, longer duration. So I think I've addressed the question. Operation and maintenance, that's the and we have also an operational center in Sweden that monitors all of the plants in the world, and we send data backwards and forwards from the installations to the operational center in Gothenburg in Sweden.
Thank you very much. So I see that like the questions are just continuously flowing. It shows so the amount of interest we have actually from the audience. And so I would like to stop here, and I guess Torbjörn, you've done a fabulous job trying to answer the questions. I would also kindly ask you to follow up on the questions by typing typing the answers for the questions that that haven't been addressed, since we need to move forward with the second presentation. But I would like to make my final remarks. I see the potential of this technology because it's so scalable, and it actually serves a lot of different business use cases. Like we actually see a lot of these needs for clean energy, not only on the utility scale, but also in the community level and even in the rural level, where we have energy needs, clean energy needs in agriculture and mining, etc., where we can actually think about expand the concept of agrivoltaics, where we can actually deploy a significant amount of solar PV, which we can actually use the thermal energy storage coupled, so that we can actually provide clean energy for agricultural purposes. I mean, this is like one of the business use cases that can be developed. And in fact, like the system has to be designed based on a case-by-case basis. So we don't have an answer that is going to be a one-size-fits-all. So this we would have to have like detailed discussions on the system design at a later stage. So I will stop here. Now I would like to go to the second presentation, where we actually have Michael Geyer, who is going to be presenting the synchronous pumped heat electricity storage from Malta. Since 2018, Michael Geyer is Malta's Managing Director for Business Development Europe and MENA. He's also the Senior Advisor for the German Aerospace Center in the field of development of thermal energy storage for Carnot batteries, including many other experiences. In this period, he participated in feasibility studies on giving coal plants in Germany and Chile a second decarbonized life by converting them into storage hubs for renewable energy. I would like to pass it on to Michael, and I would really like thank Torbjörn for the excellent presentation. Thank you.
Thank you.
Michael, you're muted.
Sorry. Okay, so do you all see, thank you for the nice introduction. Do you all see my screen now?
Yes, we do. Thank you.
Oh, okay. So here in the second part of the webinar, I would like to present you, let's say, the other end of the scale that Torbjörn showed, and that is the utility scale long duration synchronous electricity storage for the energy transition. And I have here prepared basically the following content. First, I want to introduce shortly Malta, and then I would show what is the role of thermal storage for closing the gap between the short duration and the seasonal storage needs. And then I've been asked to give two practical examples where we have been working. The first is the case of Spain. Secondly is the case of Chile, of the repurposing of coal plant. And finally, I want to present you how the Malta pumped heat electricity storage works and what kind of application it may have for you, and also including performance and costs. So, yeah. So first of all, a short introduction to Malta. Malta is offering a breakthrough storage system that basically uses the world proven molten salt thermal storage system and makes it available beyond concentrating solar power for here electrical variable renewable power generators as PV and as wind. And basically what it does is it converts first the power into heat, and then it does it by a heat pump principle. We add a cold storage level in coolant tanks and pump the heat then from the cold tanks to the hot tanks. And so this is being done with a coefficient of performance of some 1.4, and then it is reconverted into electricity and can deliver electricity and heat. So it can be from 10 to some 100 hours. It is a utility scale. It is synchronous, has a long lifetime, and no degradation. And it is competitive. I will show below $200 per kilowatt hour long duration energy storage capacity. Now, sorry. Yeah, here is first of all here also Malta. Malta is a technology spin-off of Google. Google X was founded in 2018, and its initial investors have been Breakthrough Energy Ventures, and the technology investor is Alfa Laval. And to this, in a second series, have added Proman, world's second methanol producer, and Chevron and Piva. And Malta has a strong commitment also in Europe, where it has affiliates in Germany and Spain, and it is founding member of the Long Duration Energy Storage Council. So when we hear of storage today, most people think storage is pumped hydro and is battery storage. But if you look on the world, what is installed, apart from the pumped hydro is 95%. So the remaining 5% of this, let's say almost half, is thermal storage, and the other half is electrochemical. And the thermal storage is practically all molten salt storage and concentrating thermal power plants. So just to give you an impression on the track record, that is worldwide currently is installed some 22 gigawatt hours of such high temperature molten salt storage capacity, with a total discharge capacity in these concentrated solar power plants of some 3,000 megawatts. Most of it is installed here in Spain and in MENA, and so it has a long track record and is already mature, bankable. And here I just want to show how this can be expanded then to the beyond this concentrating solar power, to the wind and the PVs. So basically, in these molten salt storage, thermal storage system, energy is how is energy stored? It is stored in a mixture of nitrates, of potassium and of sodium nitrates, where there is a cold tank at some 270 degrees centigrade and hot tanks up to 560 degrees centigrade. And this material in its, let's say, other life is just one of the world's most abundant fertilizers. So it is completely environmental harmless. It has no degradation. And at the end of its lifetime, it can either be reused in a subsequent storage system, or it can be deployed as a fertilizer. Now then, here this thermal heat is then reconverted to electrical power or to heat in a rotating in rotating turbines, and in the concentrating solar power plants, these are steam turbines, and in the Malta solution, these are closed loop Brayton cycle gas turbines with air as the fluid. And so basically what it does is that here power is converted into heat is stored, and then heat is reconverted in power. And since it is done with synchronous machines, it is reconverted into synchronous power and into heat as required. And with this property, renewables plus molten salt thermal storage can substitute gas turbine plants or other thermal power plants in their flexibility and in their ability of providing services as synchronous power, short circuit current, etc. So this is given here by the Long Duration Energy Council. Apart from energy shifting, these kind of storage systems provide synchronous inertia and here other grid services. Now, also to see what kind of size we are speaking, the largest molten salt storage system complex is now currently being constructed in Dubai, and that is a 700 megawatt concentrating solar power complex with a total with 12 to 15 hours of molten salt thermal storage. So 700 by 12 is almost 10 gigawatt hours of molten salt thermal storage that are currently being constructed and financed in project finance, and yielding a total tariff of some $73 per megawatt hour in a 35-year power purchase agreement. So what this gives you is this technology, first of all, is a utility scale, and the lifetime here in commercial contracts is up to 35 years, and its storage capacity is here up to 15 hours, and this is what we are building on. Now, the let's say nice thing of it is that here both of the most important storage technology and storage media, which is the lithium for the lithium batteries, or which are the nitrates for the molten salt storage, they both come here from the Atacama Desert, and they are in some cases jointly mined in solar evaporation ponds. So here the Earth gives for both storage system, lithium, iron, and the molten salt storage system, its basic materials here. This is one of the places. And the good news today is that let's say here the renewables have dramatically fallen in cost, so that here this is the IRENA table of private power private auctions on power purchase agreements, and PV had reached now record lows of some 1.04 US cents per kilowatt hour in Saudi Arabia, but also in Portugal, in Europe, it got down to some 1.12 euro cents per kilowatt hour. And this means today that if we combine the variable renewable energy like PV or wind with storage, we can get dispatchable 24/7 power that is, not only that is competitive and can give us, let's say, a low-cost energy solution in the energy transition. Here, what I just wanted to show is, let's say, the difficulty which we have when we develop storage projects. We only look at the discharge part of the storage, and that means how much does your discharged electricity cost? And then here, the range today is that discharged electricity is somewhere plus minus $100 per megawatt hour. And then let's say there is mostly a reaction that says, wow, that is much too expensive. And therefore, let's say people have not invested in storage. But what one has to look in is not only, let's say, the discharge period, it's basically the entire 24/7 generation cycle. And here I have put this in the time of day. During the day, we have seen we can generate and inject directly wind and or solar PV electricity into the grid for less than $20 the megawatt hour. And then if we charge part of it, the storage, then at the night, we probably will have some LCOE, which are 100, 120 in this range of dollars per megawatt hour. And if we look what is the average, because over the year you have 50% night hours, 50% day hours, then if you add the 20 plus be conservative, the 120, you then are at an average of $70 the megawatt hour for fully dispatchable, clean CO2-free electricity. Now, this average price in the past still was above what was the market price of fossil generation without CO2 tax. Just give you the example here in Europe or in Germany or Spain. Here, fossil generation was in the order between 30 or 40 euro per megawatt hour. So if you were at some 70 average price, then this was considered as being twice as expensive. But meanwhile, this average fossil price is raising. And the one thing is due to the CO2 tax, but the other thing has been in the recent year, the market. And just to remind you, here in Europe, the gas thermal price went up to almost 300 euro the megawatt hour thermal, which at 50% combined cycle efficiency would be some 600 euro the megawatt hour electric, which in some hours of the year has been charged. Now it's back to some $100. But this means that the general joker of electricity, or securement of electricity supply, the gas-fired combined cycles, have now well lifted, let's say, above the 100 euro or dollar per megawatt hour range. And that now our average price, if we combine the renewables with storage, is well below the price for the fossil generation. So I think that is the good news, that here 24/7 dispatchable renewables with storage is today more competitive than the fossil energy, and is an option to substitute, not only to exit coal plants, but also substitute gas-fired power plants. So just to give you the example of Spain, here where I'm located now in Almeria, southern Spain, where I had developed the first parabolic draft plants under 1, 2, 3 with 7.5 hours of molten salt storage, 50 megawatt each. So in the national plan, Spain by 2030 aims to reach an annual share of some 74% of renewable electricity. This will require some 57 additional gigawatts of new renewable energy capacity, and it will require 6 gigawatts of new storage, 3.5 gigawatts of pumped hydro, 2.5 gigawatt of battery, and 5 gigawatts of concentrated solar power with at least 6 hours of storage. And here you see that's a study of Bloomberg. No, sorry. Yeah, of Bloomberg. And you see that while this is built up, here the let's say the hours where you probably will have curtailment of solar power will steadily increase. And this will increase, let's say, the need of storing this electricity in order then to discharge it in the hours when there is no sunshine. Now, why is there, let's say, a special need for synchronous storage in countries like Spain? And this is basically because from an electricity securement point of view, the Iberian Peninsula is kind of an island grid. And we also had done a study here for Germany. Germany is more or less sitting on a copper plate, and if they have some sudden fallout of a couple of 100 megawatts, they can get electricity from the north, from Denmark, from France, while here in Spain, the total connection, I mean, Spain has a system, will have a system of some 93 gigawatts by 2025, 125 gigawatts by 2030, but its interconnection with Europe currently is 2.8 gigawatt. That is less than 5% of its capacity. And by 2027, they they plan to add a submarine cable and add another 2.2 gigawatt, but then it will be 5, which still is less than 5%. And therefore, countries who are not interconnected with neighboring countries, and they need a reserve capacity that grants the stability of the grid. If some of the large power producers are suddenly a disconnection, or if for some storm there's a transmission line disconnection. And that is why here for the Spanish grid, the Spanish system operator, Red Electrica, in its recent planning that was published in September last year about the next 5-year plan on future grid access capacity, is world's first transmission system operator, which distinguishes in this grid access capacity between synchronous generators like and non-synchronous generators like wind and PV. And it shows that here, for example, there is a grid node where the total capacity available is 638 megawatt, of which 432 can be non-synchronous. But this means that here some 200 megawatts are only for synchronous generators. And if you sum this over all the Spanish grid nodes, there is almost 15,000 megawatts of capacity that are available for synchronous generators. And that is what Malta is offering. And here, for example, there will be a nuclear plant closed down, etc. There you have regions in Spain where you have the danger or the risk of tension holes. And these are, let's say, exactly the regions where you also have most of solar power. So that is why, let's say here, first of all, here is a program for 5,000 megawatts of CSP with storage, because these will be synchronous generators. And that is where also here we are developing a project, 100 megawatts here in southern Spain at a substation that has some 600 megawatts, of which 200 need to be synchronous. And that is where also the EIB has now contracted, has awarded us a project development agreement, and has contracted an independent consultant, Rambald from Denmark, to do the due diligence on the performance and the production and the technical performance of our system. The other example which I wanted to give you is where I have been involved here together with the DLR in a study here of repurposing power coal plants in Chile. And first of all, Chile is the country in the world which has best solar radiation. It has over 3,000 kilowatt hours per square meter a year. And here in the north, where you have best radiation, is 5,000 megawatts of coal plants. And I find this example interesting because it's, let's say, a way that is the other way that is you find normally in the world. Normally in the world, you have coal power plants, and then you transform them to gas-fired plants in order to decarbonize. Here in Chile, they originally, the power plants had been gas-fired power plants until 2005, when Argentina cut the gas supplies, and then Chile had to develop a new power supply base for its copper mines in the north of Chile, and they tendered these coal plants from 2007, 2008. And the interesting thing that is all private financing, and there were power purchase agreement around, I think, between $80 and $100 the megawatt hour for coal electricity in 25 years power purchase agreements. And the first plants got to grid in 2012, 2013, and the last one in 2019, so they are brand new. And while these were, let's say, connected, renewable power dropped from over $100 the megawatt hour to, let's say, below $20 the megawatt hour, which then, let's say, motivated large consumers, and this is a slide from the Chile Energy Ministry, to revise their private power purchase agreements. I mean, they were paying something like $90 the megawatt hour, and the market offered 20 for renewables. And then they were looking for what is called the early termination clause. And they decided that it was economic for them to cancel, for example, 450 megawatts of coal power 77 years early and pay an early termination fee of 840 million, and to have, let's say, a more competitive or more economic power supply, and at the same time, let's say, be environmentally decarbonized. So this shows you in a fully private, let's say, capitalistic financing environment that renewables get cheaper today, and that, let's say, there is to exit coal is a way not only to decarbonize, but also, let's say, to have an economic, interesting solution for the consumers. Now, the other way.
Michael,
Yes?
can we wrap up the presentations within 5 minutes, please? Thank you. Yeah.
Okay, so let me give here the option here is to add molten salt storage to these new power plants and to provide new storage hubs in the former power plants, and that is also something which Malta is offering, and Malta is studying, and so we are analyzing this in the United States together with Duke Energy to convert coal plants into storage plants. Now, let me just give you here an introduction to the Malta system. The Malta system is a 100 megawatt molten salt and coolant storage system that has turbo machinery to work as a heat pump for charging, and turbo machinery to work as a generator at discharging. And here this provides you, as I say, 10 to 100 hours of storage. I will not go here into the technical details, but I just want to show you, first of all, how can you connect this here to the system. You can you have the discharge as a synchronous generator, 100 megawatts directly connected to the grid. And you can charge this via the grid, or you can charge this directly with a connected wind or PV plant. And the good thing is you can scale this up from 10 to 100 hours by here multiplying the number of the tanks and also replicating the number of the charge and discharge cycles. So you can scale it up from 10 to 100 hours, from 100 to 1,000 megawatts, and so have a real replacement for gas-powered plants. Finally, here the cost is what I have just what I had told you. The capex is very competitive, and the longer the storage, let's say, it goes down here. The first systems with a here 8 hours of storage have a capex of in 2022 USD of some $260 per kilowatt hour. And here, when going to 16 hours of storage, goes below 150. At 24, you are approaching 100. And if you go for multi-day storage, you are approaching the $50 per megawatt hour. So that is basically here what I wanted to show you is that today, combining utility scale synchronous thermal storage with variable renewables offers a competitive solution to replace gas-fired power plants and to repurpose coal plants, and to decarbonize your system and have and go to the energy transition. Thank you very much.
Thank you, Michael, for the excellent presentation. This is really great. Seeing a lot of these different technologies, even in the thermal storage group, basically covering the whole aspect of the energy sector, all the way from the utility scale all the way to the end user. It is in fact really like very like for me it's really, I'm glad to see that we see a lot of these advancements in the technologies, and also in fact as a we call electrical engineer myself, we have always been talking about issues related to the lack of synchronous power in the system. Well, this is actually this could be one of the actual solutions that could provide the synchronous power, which would be needed in renewable heavy energy mix in the future. So I would see that like Malta would play a significant role in the decarbonization of the power market. So I have a couple of questions that we have being posted. So there is a question from Kingsley again. So he asks, long duration storage is often seen as a long-term strategic asset with sizable investment and long payback like nuclear. Thus, it is not seen as an attractive short investment. Is my observation accurate? So I would like to pass it on to you, Michael, for your observations, please.
Well, I don't think that this is comparable with nuclear at all. What I have seen myself, let's say, in the development of concentrating power plants with long duration storage in geographies from Spain to South Africa to Chile to South America, they have, I mean, you would need like a 20-year power purchase agreement. And then this is like any other renewable project, like any large battery project, which has, let's say, a payback time in that type of period. There are also models where you have, let's say, shorter term private power purchase agreements by which you can then finance these kind of systems, and partly also sell just into the daily market. So I don't see that there are, let's say, long payback periods as in the nuclear industry at all.
Yes, thank you very much, Michael. So there is another question from Fernando, and the question is, has Malta found challenges in heat transfer between molten salts and the Brayton cycle working fluid? Heat transfer from a higher BP molten salt to gaseous air is not a common practice in CSP, as intermediary heat transfer fluids are used, but this would reduce efficiency. So Michael, over to you.
Yeah,
please.
just to hint that in the CSP industry, the latest generation plants, they have the heat transfer between molten salt and high pressure steam, which is a gaseous medium, and they are not using the intermediate heat transfer fluid oil that the parabolic draft plants have. And it is just that here the heat transfer between the molten salt and the air is, let's say, simpler and less risky than from the molten salt to the high pressure steam. So in this respect, we have a more comfortable solution.
Thank you, Michael. There are two more questions, and I think I would wrap it up with these two questions. There is a question from Ricardo where he says it is curious that when talking about thermal energy storage systems, there was no mentioning of concentrating solar thermal technology systems as a renewable energy source, and only photovoltaic and wind energy were mentioned. Could either of the two speakers explain the reason for this?
Well, first, I think I spoke quite a lot of time on the concentrating solar systems and have indicated, let's say, their enormous role today. There are places where here, like I would say, Chile, with high radiation, where CSP will be, or South Africa, or parts of Spain, where CSP will still be, let's say, the most competitive solution. That means heat the salts with mirrors. But there are many places where, let's say, with the lowest cost of PV going down, approaching the $10 the megawatt hour, there it is cheaper, and where the direct normal radiation is not so high, it is cheaper to heat the salts with windmills or with PV than with mirrors. And so it doesn't mean either or, it just means that we can use these systems now in geographies where you would not put CSP plants.
I mean, I could add to that as well. We have initially, in the first phase of our project, because we came from a CSP concentrated solar power dish powering the Stirling engine, we wanted to kind of use that heritage into the storage technology. So we investigated a lot of effort and money into finding solutions where we could actually charge our systems with concentrated solar power, either by a dish or by a heliostat field that you will find in many of the CSP installations today. But there are many reasons why we did not go down that route, and that's mainly because it's difficult, limiting the market, it's expensive, and the fact that PV panels and electricity from those are so much more accessible around the world, and the cost of electricity from PV is very, very competitive with anything from concentrated solar power. So to widen up our market and to drive costs down, we abandoned the CSP and we just went with electricity powered units only. So we're not considering CSP anymore, but there might be applications where they're more cost competitive, but not for our case.
Thank you very much, Torben. So the final question for this session, and then I will give some time for the speakers for the final remarks. So there is a question from Sergey. Could you elaborate a little bit more on why this capital specific cost increase with size? It sounds counterintuitive. So over to you, Michael, please.
Yeah, I mean, just if I add here, the capital specific cost increases with size because you have to add tanks, additional storage volume. However, if you look here, when you go in let's say in batteries, they go more or less linearly. If you go here from 8 hours to like 80 hours, you do not go 10 times. This means from 2 to 20,000, but you only go from 2 to here 80, something like 4,000. So when you do 10 times the storage volume, you only have twice the investment. So that is, it increases, that is the absolute capex. That is the absolute capex. Yeah, that is the absolute capex for the for this 100 megawatt system. So if you have 8 hours of storage, if you have multiplied by 10 times the same, let's say, power of storage costs you twice as much and not 10 times. And this shows that if you look at per kilowatt hour, it reduces. Here it reduces from to a fifth, more or less. Does that answer the question?
Yes. Thank you for the clarification, Michael. And I think we are done with the question and answers, the Q&A. Now I'll pass it on to Torbjörn so that he can actually speak for 1 minute on final remarks on thermal energy storage and how he sees the way forward on the market and any final remarks.
Thank you. I mean, first of all, thank you very much for the opportunity to share my insights from Accelio and thermal energy storage. I much appreciate that. And I think just a final remark is that there's so many initiatives out there with long duration energy storage. We are one solution, and we're now in the kind of the third valley of death for such companies. It's like now we want to commercialize, we want to build capacity. But both Michael and I, we kind of point out, and Juliet and yourself have said that the rate of long duration energy storage for the future will have to be exponential. We have to do something jointly. So the cost, whatever you talk about, we need to build the base and to build as many technologies out there as possible, because we need to fill that gap. Because pumped hydro will not solve everything, and batteries will not solve everything. So we need many technologies in there, and we need investments to cover for the commercial projects, because the money we are raising from our investors is just not enough to fund the initial phases until we are well established on the market and we will be a technology provider only. So that we are asking kind of the banks and investors to fund the projects going forward, and to build the base and to ramp up the volume capacity and manufacturing worldwide. So I think that's my final note, to say that long duration energy storage is there for many years to come, but we need to get over that final hurdle to fund it. And that's why when the World Bank is just one of the players in this worldwide. But thank you again for your opportunity, and all of you having listened to our presentations.
Thank you so much, Torbjörn. So Michael, 1 minute on your side.
Just fast. Also, thank you very much for the opportunity. I think, let's say, we are now at the right time. That, I mean, the world needs the transition, and for this it needs the storage. I think, let's say, the biggest hurdle is probably not the inertia of the storage system, but probably the regulatory inertia to enable, let's say, renewable and storage systems to be considered in the market. And as we have seen in the introduction of the renewable generation with feed-in tariffs, with World Bank tenders, etc. We now have to again replace 30 years of fossil fuels by an initial, let's say, technological investment, now not only into the generators, but into the storage. And so I think we need long-term offtake schemes that would guarantee the revenues. And I think then the developers and industry will take the risk, let's say, to build it. I think investment money is there, but we are not there yet that, let's say, in the tenders worldwide or in the markets, long duration 24/7 offtake agreements are considered. So far, only it's considered tenders for power, but it isn't said you need to guarantee the supply here during nighttime, etc. I think this is what we have to introduce, and then I think this will open the industry developers, etc., will come and bring LDS into the market, like have been PV and wind being brought into the market with such kind of tenders and contracts in the past. Thank you.
Thank you very much. I think we've gone 1 minute past our allocated time, but I would like to give a million thanks to both presenters, Torbjörn and Michael, and hope all of you have a great day. Thank you so much.
Thank you. Excellent.